It's my great pleasure to introduce our today's speaker, Roger Melko. He's a professor at the University of Waterloo. Uh, he is also Canada Research Chair in Computational Many-Body Physics and Associate Faculty at the Perimeter Institute for Theoretical Physics. He received his PhD at the University of California, Santa Barbara in 2005. And his research involves the development of computer strategies for the theoretical study of quantum materials, atomic matter, and quantum information systems. We have a great pleasure to see you here at our seminar. And please, Professor Melko, the floor is yours.
Okay. Thank you very much. So let me share here, and can you confirm that you can see that page?
Yeah.
Great.
Great.
Okay, thanks so much, Andre and Sergey, for inviting me for this wonderful seminar in Kharkiv. It's a distinct pleasure to give this talk, and thanks, for the pronunciation of my name. I wrote my name here in Ukrainian because a little bit of background for myself, and thanks for the wonderful introduction of my professional career. But in my personal life, my grandparents are from Western Ukraine. So my grandma's from Volyn, Kamień-Kazierski, kind of up in the northwest. And my grandfather is from Lviv area. And I've actually been there to visit in 2001. So it was fun to connect with some of my family. Some of them who are now have traveled to Canada and are living with us here in Canada. My grandparents moved from Ukraine to northern Manitoba, which is where I'm from. And as Andre said, I did my PhD in University of California, Santa Barbara. So I moved actually from Manitoba to University of Waterloo for undergrad, which is here. Moved to University of California to do my PhD. And then I did a postdoc at Oak Ridge National Labs, which is famous for its sort of leadership computing facilities. So I'm very much a computational theoretical physicist with a computational slant to my research. After my postdoc at Oak Ridge, I moved back to the University of Waterloo as a faculty, and now I'm faculty at Waterloo and also the Perimeter Institute for Theoretical Physics. So, again, it's a great pleasure to be here to talk about language models for quantum computers. And just by brief sort of a way of outline, I'll kind of gently introduce the concept of language models, maybe in the broader context of artificial intelligence. And then I'd like to kind of take the perspective of using language models based from artificial intelligence and machine learning for learning quantum states. So the idea is that we'll take data from quantum computers and basically train language models. And what I hope to convince you of in this seminar is that the combination of data and data coming from quantum devices and artificial intelligence like language models is presenting us with what we call a virtuous circle or a virtuous cycle, where we can enhance the development of each technology using the other. And so that'll be kind of the end of my presentation. And feel free to interrupt. I love getting interrupted just to know that you're listening, and also to help clarify any points of discussion and so on. So feel free to stop me at any point if you think this is going off the rails. So I think we're all used to the idea that we're in an interesting age of artificial intelligence. We've seen rapid developments. I won't go through sort of the history of it, but as Andre and I were chatting before the seminar, we have a mutual friend working in Silicon Valley who I was speaking with last week. And I was actually surprised to learn that many practitioners and many developers of artificial intelligence in Silicon Valley are openly talking about the so-called singularity. And the singularity is an event, where also, I don't know exactly how it's defined. People define it different ways, but it's certainly an event that has, all sorts of wide-ranging changes for how humans and computers interact. Let me put it simply that way. And it's an interesting idea that actually dates back to kind of the dawn of the computer age. This is an amazing photo of John von Neumann, of course, one of the fathers of conventional computing, as well as quantum physics. Richard Feynman in the middle there, a young Richard Feynman, who we're used to, I guess, attributing the idea of quantum computers and quantum simulators with. And Stan Ulam on the right-hand side, who is famously an alumni of Lviv University in Western Ukraine, who also was a father of all sorts of technologies, including Monte Carlo, which is one of my favorite techniques. And so Stan Ulam is attributed with a quote, or sort of the idea of the singularity he attributed to John von Neumann. One conversation centered on the ever-accelerating progress of technology and changes in the mode of human life, which gives the appearance of approaching some, quote, essential singularity in the history of the race, beyond which human affairs as we know them could not continue. So this idea, it's interesting that these three gentlemen and the people that worked with them are in some senses talking about things like quantum computers, like artificial intelligence, like the singularity, that are still in vogue today. So the reason for optimism around this idea, the idea that there's some sort of rapid change occurring in our interaction with technology, very much comes from modern language models. And I'm showing some results on the right-hand side that you can look at, sorry for the low resolution, from a recent paper, maybe was it a year ago, from OpenAI's GPT-4 program. And what are these language models? So on the left-hand side, I kind of have a very rough organizational diagram, for generally the field of artificial intelligence, that I've divided into, discriminative or discriminators and classifiers, and generative models. So on the left, the blue are supervised learning techniques, and on the right are unsupervised learning techniques. Supervised learning techniques are typically employed in things like computer vision. When I want to identify, the simplest thing that you could do is to maybe upload the pixels of an image, representing a cat or a dog, and I can ask the artificial intelligence or the neural network to classify that image. Is it a cat? Is it a dog? So that type of classification usually happens through some supervised learning architecture, like a feed-forward neural network, a convolutional neural network, something like that. On the right-hand side, generative models, which will be the focus of today's talk, very much are unsupervised learning architectures. So it means that there's been no supervision or labeling of the data. And the data that's fed into these unsupervised learning models is typically used to, in the base level, to learn the probability distribution of the likelihood that underlies that set of data. So for example, if I feed into an unsupervised learning architecture all the pictures of dogs that I can find on the internet, what I will learn in some sense is the probability distribution that underlies pictures of dogs on the internet. And so it seems a little odd to say it like that, but in the quantum context, I think it makes a lot of sense, and you'll see more about that. Language models are the subset of generative models that have arisen recently, including things like GPT, ChatGPT, and so on. And these are the generative model architectures that have led to all this excitement about things like the singularity. And the reason is sort of these step changes in performance. So the blue, is GPT-3 and the green is GPT-4, if that's right. I have this sort of covered up. Yeah, that's right. And you can see a huge jump in the accuracy For example, in AP physics tests, which, for previous versions, we're getting somewhere around 30% accuracy, and now we're scoring closer to 70%. So somehow these language models have basically solved the problem of how we do, physics in this simple case and so on. And so in some cases, like the bar exam, these models are, performing well enough to basically be admitted into top universities in the US. And so again, something is certainly happening inside of these language models. And I'll talk a bit about, what we think it is. So one of the, I guess, prevailing wisdoms about language models, and I'll talk about the architectures in the next section, is very much that they are scaling to a large degree. And so I'll define what makes up, the parameters and so on of a language model. But as you make these models larger and larger, and I'll explain what that means, we're at the cusp of observing changes in scaling and emergent phenomenon. So I'm a condensed matter physicist by trade. We're used to discussing the concept of emergence, maybe in things like, high temperature superconductivity, or things like that, macroscopic quantum phenomena that emerge from microscopic interactions. The term is now being thrown around quite a bit in large language models and LLMs, where very large data sets and very large amounts of compute have seen step changes in the abilities of these models. For example, so I'll talk about what tokens are and so on, but here's a loss function of different language models for different numbers of parameters in the language model. Okay, so here's 10 to the 3 and here's 10 to the 9. And what you see is that the loss or the performance, basically improves very rapidly for the amount of tokens or words that are processed through this language model when it's much larger. And so larger models seem to do better at learning than smaller models. And by large and small in this case, I mean the number of parameters that are used to represent the probability distribution. So on the right-hand side are the accuracies of certain, I've pulled them from one of these papers, of certain tasks like modular arithmetic as a function of model scale, by which I mean the number of floating points, like floating point numbers that have been pushed through those models in training. So the training floating point operations, okay? So, and look at these numbers, they're staggering. As you get past about 10 to the 22 or 10 to the 23 floating point numbers used in training, you see very large step changes in the accuracy of some of these large language models. And Lambda and GPT-3 and so on are just different variants of these large language models. So these step changes in ability are now, again, very much bringing the idea of emergence to the forefront, where emergence is when a quantitative change in the system results, in qualitative changes in behavior, which people are talking about, but we really attribute all the way back to Phil Anderson in the 70s, talking about more is different in condensed matter physics and so on. So these results make us wonder, is scale really the main ingredient that is allowing us to approach these step changes in ability? And breakthroughs in scale arise from 3 different things in these models: the parameterization, which I'll talk about what that is. It's the number of the number of numbers that are used to represent the probability distribution in a generative model. The amount of data that is available, right? So out there in the world, if you want an English to Ukrainian translation system, how much data can you get off the internet to help train that thing? And then compute is, how many different training iterations you can afford to do, basically. So GPT-4 contains 1 trillion parameters. It means the size of that model, is stored on a hard drive or a USB stick, is basically 1 trillion, probably single precision floating point numbers. I'm just guessing, it might be double precision. Training, as I showed in the previous slide here, involves 10 to the 23. So Avogadro's number of floating point operations. So that's incredible. Like as a physicist, if you think of going from, a microscopic scale up to 10 to the 23, it's maybe no huge surprise that we see emergent properties, but it's amazing that these architectures are getting there. The cost of compute is very significant for these models. So GPT-4 costs 100 million to train. I've heard of European large language model startups that have something like 50,000 GPU cards used for training, right? So they've really kind of reached an economic scale, if you want to call it that. There's scaling to these things is not just a scientific endeavor, it's certainly an economic endeavor. And essentially the data, the amount of data that's going through these models is approaching the entire internet, okay? And so the combination of all these things together, and especially the amount of compute required to scale language models is evident. You can just see it in NVIDIA's market capitalization. So their market cap, which I just pulled off the internet somewhere from Bloomberg, you can see is essentially passing, although they had a bit of correction in the last few days, but NVIDIA is basically passing the market cap of Microsoft and Apple because NVIDIA provides the GPUs that are used in training for a large number of these models. So again, this just gives you, if I knew nothing else about the world and I looked at the curve of NVIDIA's, stock price or something like that, you would see that something is going on in the field of artificial intelligence. And so I just want to end this section by saying, there's many parallels between what we see in artificial intelligence and what we hope to achieve in quantum computing. And particularly, we aspire to achieve quantum computing at scale. And when I mean at scale, I mean really at the scale, like, the computing has been achieved in your phone, right? Where you have trillions of transistors, you have $100 billion invested every year in silicon technology, like in terms of fabs, and so on. So there's a whole industry built up in order to scale classical computers. We're building an industry around artificial intelligence, and this is what we're trying to do with quantum computing. And the reason is we need quantum computers with large numbers of qubits and gates. And, part of that is because of this man, Peter Shor, and his algorithm, Shor's algorithm, which will break RSA encryption. So if I have a 2048-bit RSA key, I think at minimum I need something like double the number of logical qubits to crack that. So something like 4,000 logical qubits. And then the logical overhead for error correction, so physical to logical, might be 1,000, might be 10,000. So in order for Shor's algorithm to be implemented in a useful way, we need of order 5, 10 million physical qubits. And that's just the beginning, right? So we're nowhere near there yet. We have a lot of work to do. If I want to solve other problems, like less, cracking RSA and more quantum simulation, again, I'm a condensed matter physicist, so somehow our holy grail is the Hubbard model and maybe solving the Hubbard model by implementing it in a highly controlled quantum simulator. Again, you have to be able to beat conventional simulation techniques, which occur at scale on our conventional computers, right? And so there's a huge number of qubits and operations required for this. So just like in artificial intelligence and in the silicon industry, scale is partially a scientific and technological question, but also very much an economic question. So do we have the economic incentives to build quantum computers at scale? And do we have kind of the tools and so to do so? And so I'm also very interested in this kind of economics question. I spent a lot of my time with the Creative Destruction Labs. It was just an incubation stream for quantum startups in Toronto. That's where I met Mykola Maximenko and the famous Ukrainian startup Haiku. So very interesting work in that domain going on, I think out of Lviv these days. So very much an economic question. And, just like large language models, like, ChatGPT, have sort of reduced the cost of certain things in our lives. We hope that LLMs can also be integrated to help reduce the cost of quantum computing in order to achieve scale. And again, that'll be through design, maybe characterization of computers, and also control. So for the next two sections of the talk, I'll talk about a little bit about the architectures, because I've been throwing around ideas like parameterization and size and so on. I just want to put that on a bit of a firmer footing. And then I'll show some examples of how we train with quantum data. So maybe this is a good place to pause if there are any questions about my perspectives on AI.
Yeah, please. May I ask a question? So you mentioned that you essentially train now with the whole information available in the internet. Does it seem that we have met the upper boundary, so we cannot proceed further, or it can self-generate somehow increase amount of information to train further?
I think there's still some hidden pools of data that people are tapping into. So Slack was a big one. I use Slack with my group, and we have 150 members. And we just heard a couple of weeks ago that all of our data has been sold now, to use to train LLMs. So I guess there's always these hidden pools of data. But then eventually, I believe generative models will generate data that will be used to train the next cycle, which is perhaps worrisome, but also, I think, inevitable. So yeah, I think you're right. I think generative models in some sense will replace our data. And one thing that I'm pushing is that we also have a data source in our quantum computing devices that can be used for this. So yeah, data is the new oil. It's kind of an old meme, but I think it still applies.
Yeah, please, Dennis.
Yeah, hello, Roger. Nice to meet you. I'm myself a graduate from University of Waterloo. I got PhD in 2011. So there is a connection between actually Kharkiv and transformers, very close connection. The famous paper, All You Need Is Attention. The last author is actually graduate from Kharkiv Polytechnic Institute.
Oh, I should have put the names up. I didn't.
Yeah. So just wanted to mention that. Thank you.
That's a great connection. Thanks so much. I'll get to the transformer, but thanks for that.
I have a question.
Okay.
Yeah. So you have mentioned that large language model can help us in achieving scale for quantum computing. What do you mean by that?
Oh, that's the entire rest of my talk.
Okay.
So I hope that's what I want to explain.
Okay, thanks.
That's a nice point then to proceed, I think.
Perfect. Yeah. Okay, great. Okay, so I think sounds like we're all on the same page here. So let me talk a little bit about the architectures and what makes them interesting and what makes them powerful, perhaps. And then we'll go on to how we can use these architectures to speed up and scale quantum computers. So I'm kind of backing up, and I said a lot of words in the first section, and so let me go back and reiterate some points, for the audience. I think so. Generative models. So when I talked about unsupervised learning, generative models, language models, let me step one circle back and say, what are generative models, and what's the typical setting that we use generative models for? So generative model is used to learn an approximate probability distribution, okay? An approximation of something that occurs in a black box. I'm calling it P of X, and P of X is unknown. So the functional form of this thing is unknown. Maybe it's the probability that I'm going to pull a picture of a dog or a cat out of the internet or something crazy like that. So it might not even have an explicit form in some sense. But what it does, what you can do is you can query the black box to produce data sets. And so I have my data sets labeled as X1, X2, X3. Each one of these is a vector. And, there's n bits, say, let me just think of something simple like a binary black and white image with n pixels, or n projective measurements coming from n qubits on a quantum computer. Okay, so I'm going to use these two things interchangeably. And a 1 or a 0 could be a black and a white in an image, or it could be a qubit SZ state up or a qubit SZ state pointing down. And I have 1, 2, 3 vectors, but I can pull, tens of thousands or millions or hundreds of millions or billions of instances of X, from the black box. So this data in the generative model density estimation setting is used to train parameters in some representation of a target distribution. And I'm being kind of vague with what parameters are, but if I think of a model being a neural network, then the parameters would be the weights and biases. So here's maybe the edges of this graph might contain the weights, and those weights might be floating point numbers. And I'm just representing them by lambda. Lambda is just kind of a catch-all for all of the parameters that are occurring in the neural network. And it could be weights, there could be biases on site, there could be all sorts of matrices or vectors that are used to parameterize this probability distribution, okay? And so that's very architecture dependent. The goal of density estimation is to adjust the parameters, to learn the parameters, right? So that the model distribution is as close as possible to the black box distribution. So you want P of lambda X to be equal to P of X as closely as possible by basically doing that big optimization problem, right? Optimizing over the space of all parameters based on some loss function. And the loss function that's used for density estimation is simply the log likelihood. This comes from like the Kullback-Leibler divergence. So log P lambda X, right? If I take the expectation value, and if X is drawn from that black box, so X is drawn from P, then that estimator is a good loss function. And I could derive that for you if I had more time, but I think it's pretty standard. And so all of these generative models are typically doing is some sort of optimization or training, we call it, where the parameters, so the weights and biases of the model, are updated by calculating the gradient of the loss function or the gradient of a mini batch where I've only drawn a small subset of X from the data. So if I have 10,000 vectors here and I calculate the gradient from only 10 of them, then I can calculate the gradient from that mini batch, what did I say, 100 times, and that would be one epoch of training. And then I can throw all the data back into this bucket, pull out another 10 at random. That's, do it 100 times. That's another epoch of training. I've just described what we call stochastic gradient descent. And so the models are parameterized, through this procedure. What differentiates language models from generative models is that they're typically a subset of generative models that use the so-called autoregressive property. So it's not universally true, but it's kind of a good generalization to think about autoregressive models. And what autoregressive models do is, just to skip back here, they take the probability distribution, P of X, which is a joint distribution over all variables in this vector, so 1 to n, and they split it up into the product of conditional distributions, okay? So it's maybe a technical detail, but it's kind of important for these models. So each one of these is a conditional distribution, 1 conditioned on nothing, 2 conditioned on 1, 3 conditioned on 1 and 2, and so on. And so this chain rule of probabilities is widely used in language models. And it breaks up the joint distribution into a product of, in some sense, a one-dimensional sequence of conditional distributions, which I think is super interesting. So a couple of points is that the resulting joint distribution is normalized. So for the statistical physicists, it means there's no partition function. So we don't have to worry about things like Markov chain Monte Carlo sampling. Apologies to Stan Ulam, but we don't need it anymore, right? It's these things can be sampled, these joint distributions can be sampled, completely, IID, so exactly, and uncorrelated. So you have a normalized joint distribution, you have uncorrelated samples, but the cost is you really have to think about this, the arbitrary sort of sequence that you need to break up the conditionals in. And so on the bottom left here, I've shown a kind of simple version of a language model where I should have put in a Shevchenko poem, sorry, but I just have Hickory Dickory Dock here. So, I have Hickory Dickory Dock, the mouse ran up the clock or something like that. And the point is that I have a dictionary, 1, 2, 3, 4, 5, 6, 7 words in this dictionary. And I select one of these 7 words, hickory, and what the language model does is give me the conditional probability of the next word in the sequence, P2 conditioned on 1. So this is 1, X1. So then I have another vector here, and I've drawn from that dictionary, hickory dickory, that's my second word. And the language model outputs the probability of the next word. Dock is, occurs with high probability. If I select it, then I can keep doing that forever until I get the joint distribution. And the point I'm going to linger on this slide as I answer your question, Yaroslav, in a second, is that I can transform a language model that's used on sequences of words into a language model that's used for sequences of qubit measurements just by shrinking my dictionary down to 2 words, SZ spin up and SZ spin down, and combining the conditional probabilities, possibly with some phase information together, for example, into a wave function. So it's a very short path between sort of a sequence of words and a sequence of qubits in a quantum computer. And I'll talk more about that. Yaroslav.
Yeah, thank you. I guess in this picture on the left bottom, you have 3 conditional probabilities with different x2, x3, and x4. And what were these x2, x3, and x4?
Right. So the generative model consumes the sample from the dictionary. So the dictionary here, again, has 7 words, but x2 is the specific word that has been sampled. So x1. So x1 is literally hickory. And if this is a 1-hot vector, it's 0, 0, 0, 1, 0, 0, 0.
So in the first probability, x1 is hickory.
Right. And
x2 is whatever else you can have.
And so what's output by the model is the probability. And I have a more detailed slide next on this I can show you. But what's output is the probability of the second word conditioned on the first word.
Okay. So
if it's conditioned on hickory.
Before you go on, so these three columns at the bottom, they are 3 different dictionaries, or these are pieces of one dictionary, or?
So the dictionaries are the same in these cases. So a typical language model has like thousands of words in the dictionary.
So if I would literally do what you say with this 7-word dictionary, my capital N is 7, and I will find these P's, they're always either 1 or 0.
So N is the number of words in the sequence. So I'm imagining there's a poem, Hickory Dickory Dock, the mouse ran up the clock, something like that. There's like N could be 20 in this poem.
Okay.
So N's the size of the sequence.
Is the poem a dictionary, or the dictionary is what we see on the slide?
The dictionary is usually a dictionary of tokens. So I didn't quite get the question, but the dictionary is typically, it's not even words, it's usually fractions of a word that are broken up. So the dictionaries are typically in a language model of size thousands, and the sequence.
But Roger, look, I understand that it's more complicated than I imagined, but can you give some closed example where everything is defined? What is the dictionary? What is the?
Let me give you this example.
Okay, thank you.
Okay, so here's an actual example of a language model in the form of a recurrent neural network. Okay, so it just looks a little, obviously this is just sort of I don't know, a very rough picture here. A recurrent neural network, so I use sigma here for the state. So let me just do the quantum state where the dictionary is 2. There's 2 words in the dictionary. It's the simplest binary, sort of neural network that you can imagine. And so it's very much, I'm choosing from 0 or 1, and that's what I'm calling sigma here. And this makes the difference between, I think, the dictionary and the sequence very apparent. So I have typically a null, sample and a null hidden vector which is fed into this RNN. Okay, so a recurrent neural network structure is basically a nonlinear function. So I've just called it F here. And F is a function that takes something like weights and biases. So these are things that are learned. Okay, so weights, again, if I think of the analogy to a neural network, it could be the edges or something like that. But just think of it as a matrix of numbers, and B as a vector. And so there's a nonlinear function that processes weight matrix with a hidden vector and the sample from the dictionary, which in my case is a one-hot vector that encodes spin up and spin down, okay, plus the bias into a new hidden vector, which is output from the RNN cell. So there's many different choices for this function, and it's very complicated, and there's all sorts of tensorial RNNs and other nonlinear functions that are used and so on. But the basic idea is that hidden vector comes in, a sample from the dictionary comes in, and then I output the hidden vector of the next iteration. That's fed back into the same RNN, so the same weights and biases, or a different RNN. If you want, you can have different weights and biases, okay? So this is recurrent because, as this picture shows, I typically go through a procedure by which I output this hidden vector. That hidden vector is passed into another function here, which I'm calling S, so it's a softmax function. U and C are another set of trainable parameters, a matrix and a vector, okay? They output through the softmax function Y, which is really my conditional probability here, okay? That conditional probability can then be sampled, okay? You just sample whether or not you want spin up or spin down. So here's, again, graphically, maybe look at the second step. I input a hidden vector, I input sigma 1, I process that through the nonlinear to get the hidden vector. That hidden vector is passed into a softmax function, which gives my conditional probability. That conditional probability is then sampled, sigma 2, and then it's passed into the next iteration. I guess I should have drew it here, along with that unprocessed hidden vector, and that's done as many times as you want. If I take all of those samples from the top and I combine them, I get one of my, one instance of my sample. Let me call it, I call it sigma here, but I called it X on the previous slides. So kind of in maybe gory detail, that is a typical language model. And I could change, this was an RNN, which came from industry. I can also change this architecture to represent a quantum wave function. And one way of doing that is to just recognize that the probability of sigma that comes out of here, so the product of all the y's is the joint distribution, which is just the amplitude of a wave function. And I can also have a phase, and that phase can actually go through a very similar process, but instead of pushing it through a softmax, I push it through a soft sine, and then I accumulate all these individual phases or something like that. So I'm not going to talk too much more about any details about the architectures in the quantum case, but everything that comes from industry as a classical probability distribution representation for a language model can also be adapted to the quantum case, either a wave function or a density matrix or something like that. Hope that clarifies. Dennis?
Yeah, so the question is, why do you want to parameterize the wave function, but rather some kind of quasi-probability distribution quantum mechanics? Maybe that's more natural to do. Have you thought about this?
Yeah, you can do that. You can also just parameterize measurement outcomes. Like maybe I just want Born rule measurement outcomes, and I don't care about the phase. So there's a million different ways to skin that cat for sure. Yeah, so I guess I'm just used to doing the wave function thing, and I'll show you why. But there's definitely other ways of doing this.
Just a clarifying question. So in this formula at the bottom right for psi lambda,
Yep.
sigma has two possible values, 1 and 0, or 1 and
Oh,
9.
no, I think they're all, in this case, they're combined to get this sigma here. So, yeah. So you want one overall, oh, sorry, you said sigma, not phi. Sorry, I interrupted. Say it again. Sigma? Sigma's like the analogy of, oops, I went the wrong way. Sigma's like the analogy of X, sorry. I should use this slide. So if I want P of X, right? X is a vector, and this is, you know, however many qubits I have or however many words in my sentence is the size of that vector. So that's why I have sigma as a boldface. Does that make sense? I should have used X here. I got lazy on my slides, sorry. I'll come back to this if it doesn't make sense. A couple of things I want to note, just for the physicists out there. Of course, we have to worry about entanglement and long-range correlations and so on. And, you know, there's some criticisms about recurrent neural networks, which we use a lot, which is why I mentioned them, because they really, you know, take a one-dimensional sequence, which is very natural for languages, but they can force, you know, my spatial qubit array into a one-dimensional sequence. So, for example, if the red line is the line of the autoregressive sequence, so the autoregressive sequence is the way that I've defined this, it's very natural to define the passing of hidden states. So the hidden state is how you retain what they call context. So if you go back in your sentence and, you know, there's some context that you need to capture, this is what does it. But in a two-dimensional array, it's not obvious how you might arrange the hidden vectors, or you might arrange the sequence in order to pass the correlations and the information. So that's where the transformer comes in. So the transformer is, you know, replacing the concept of the passing of hidden states in an RNN with what we call masked self-attention. And, you know, I did put the architecture from the original paper up, but I learned nothing from this really. I think the interesting part is the multi-headed attention. And I would encourage people to look at some literature by my colleague Juan Carrasquilla, Brian Clark, and other people that talk about how the self-attention mechanism is really very much a correlation matrix, like a Jastrow factor, for any of those of you that have done variational Monte Carlo. The idea in the transformer seems to be that long-range correlations can be passed, you know, much easier than in a recurrent neural network. And so I'm going to move on from architectures, but what I do want to say is that we hope, I believe, that, you know, something in this transformer, maybe it's the self-attention that connects all of the, you know, connects all my qubits together, or maybe it's something to do with the stacking of these things and the equivalent of a deep neural network, that will somehow allow us to scale these things to capture entanglement in very large systems. So we're hoping that the success of the transformer in large language models will translate into the success of these for quantum simulation. And so the question I want to pose for the last section is, are these language models poised to make breakthroughs in quantum physics? Again, scaling is a central challenge for building quantum computers. We want our quantum computers and quantum simulators to grow very large, but it's very much an economic problem as much as a physical one. And so I'm going to argue in the next section that transformer-based LLMs could be built to help scale, you know, the number of parameters, the amount of data, and the amount of compute in order to help us with this. And there's some questions that this raises in terms of, you know, what is the best architecture? Because these are very much heuristic architectures that I showed you. But can we help guide the architectures with ideas from physics, like variational Monte Carlo, tensor networks, and so on. What do we do about interpretability? You know, when you have a transformer and I have a bunch of attention layers, you know, is there any concept of interpretability in there, and do I care? And finally, what should the data be used to train LLMs for quantum? So I'm going to focus on the last question in the next section. But again, I went through that pretty quick, but maybe it's a good place to pause. Is there any more questions about architectures and what I'm doing with language models? And maybe I'll show some results for data now. Silence is golden. So sorry for the quick blast through architectures, but you know, the idea now that I want to get into is that, you know, I've replaced language, that the problem of hickory dickory dock, with the input from a quantum device. And that quantum device, which I've alluded to, you know, is maybe a qubit device that produces outcomes, you know, from a dictionary of size 2. And it could be the SZ basis measurements, or I could have a basis setting where I've done a Hadamard gate so that I get SX or SY or something like that. So I'm imagining that I'm getting, you know, basically data sets that are in some sense, hopefully informationally complete out of a quantum device. And the one I'm showing here is QEra's vacuum cell, their vacuum chamber for their Rydberg atom quantum computers. So I'm going to talk more about that and how we use language models with that data. And that sets up the virtuous cycle. So when you're thinking about qubit projective measurement data, you have some options. And these are the 3 architectures I work mostly with. Superconducting circuits are the fastest data producers out there. They give you about 10 to the 7 shots a second, and 1 shot is one of those vectors, X or sigma, okay? And it, you know, if you produce 1 vector at a rate of 10 to the 7 shots per second, you can accumulate a lot of data. So they're kind of big data machines. I work a lot on trapped ion devices, and I'll talk a bit about open quantum design, but this is the architecture that we're building at the University of Waterloo for ytterbium ion blade trap quantum computing. Trapped ions are a different architecture, very, of course, than superconducting circuits, and they produce different shot rates, about 10 to the 2 or 10 to the 3 shots a second. So they're quite a bit slower, but there's other advantages of trapped ions. And I also like neutral atom machines. And this is me and my student, Roger Lowe, who wrote a very large part of the control infrastructure for QEra's quantum computer, Aquila, which is pictured behind us. I hope I'm not violating my NDA by showing this picture. I just wanted to convince you guys that I actually go into a laboratory once in a while. Somebody lets me in. But it's usually just to shake hands. And what I like about the neutral atom quantum computers is a couple things. They're very highly controlled, coherent devices, but they also have very slow shot rates. So these types of quantum computers, you're getting about 3 shots a second out of, maybe less. So they're actually data limited. And so I'm going to take the perspective of, you know, using that as an advantage for me, because I think limited data is kind of an interesting case to be in when we're talking about enhancing the abilities of computers with language models. But all of these types of architectures are interesting to me in terms of producing data. And so the data that comes from quantum computers is qubit projective measurements up or down. That's my dictionary for my language model. In the Rydberg atom array, the qubit, and I'm not showing too much here, is encoded in you know, the ground state or excited state. The Rydberg state is a like n equals 100 principal number, highly excited state of a neutral atom, typically rubidium 87. But there's also companies working on different atoms. But here's pictures of rubidium in optical tweezers being held at very precise, you know, distances out of Misha Lukin's group at Harvard. So a lot of the data I get comes from Misha Lukin. The optical tweezers pinch, you know, the neutral atoms in arrays that are highly, atom arrays are basically highly flexible. You can make all sorts of different geometries. I'll have the Hamiltonian somewhere, but the idea is that these things are strongly interacting due to a 1/R6 van der Waal interaction. And the qubit states are, again, the atom is either in its excited state or it's or a ground state. So these fluorescent images, like I'm showing here, are the data. The data comes out of a CCD camera, and then there's an algorithm that looks at this and tries to pick out each one of these is maybe in its ground state, and if there is a hole there, then the atom doesn't fluoresce. That's an excited state. So all of these are zeros, and if there's a hole in the image, that's a 1. And so that's the data that's coming out of these things. And I'm going to focus on, again, you can read the literature if you're interested, but these quantum computers preparing certain interesting kind of many body states that have to do, with different phase diagrams, if you will, which involve the interaction range, so how far apart these atoms are, and also how many Rydberg atoms are being tuned in there. And so, for example, I'm going to show data from the so-called disordered to Z2 ordered transition. So sorry that I don't have more time to talk about these experiments, but basically think of them as producing qubit measurements that are either zeros or ones. And here's our first foray in kind of 2019-ish into using generative models for state reconstruction. So when I talk about states, this is one of the reasons why. So this is the simplest example of reconstructing a quantum state from data. So here we took 8 atoms, so one-dimensional, and here's, well, okay, this is slightly bigger. But here's an example of data that's coming out of Misha Lukin's quantum computer at Harvard. On the left-hand side is the occupation of Rydberg atoms. And so if it's 0, everything's in its ground state, everything's fluorescing here. And I've crossed the phase boundary here into that Z2 state where I have Rydberg. That's the red circle that's representing the the 1 of the qubit projective measurement. Here's the 0, here's the 1, here's the 0. That's actual data coming out of the quantum device. This is processed into 1s and 0s, and we get 3,000 shots for every detuning parameter. Sorry, I have the Hamiltonian on the next slide, but it's just, you're varying the, is it down here? I'm varying the amount of, N is my Rydberg occupation. So I'm varying the amount of, it's like adding a chemical potential or a magnetic field that favors Rydberg atoms. But the point is that I can take this data and I can use those 3,000 projective measurements to train a generative model. And before we use language models, we use restricted Boltzmann machines, which have an architecture like this. Some of you might be familiar with them. They work very well, actually, for these small system sizes. But what they don't do is scale. So here's the Rydberg occupation number, right? So here it's 0, and here it's basically 0.5, because half of these things are in the Rydberg state and half are in the ground state, as a function of detuning. And I can compare the experimental data averaged in the black line with exact results from a master equation, because there's only 8 atoms here. And the blue is my reconstruction of the data using the restricted Boltzmann machine, using the generative model. That's fine. Everything seems to work pretty well. Why do I even bother doing this? Well, on the right-hand side is a good example of why. So for the Rydberg atoms, for a reason I won't mention, we know that the ground state is real and positive. There's no phase. So there's a 1-to-1 correspondence between P of lambda, so the parameterized neural network probability distribution, and the wave function. When I have that 1-to-1 correspondence, I can basically calculate off-diagonal estimators like the local by using this so-called local estimator formula. For example, I can get the off-diagonal magnetization, which again I haven't defined here. Apologies. But the RBM reconstruction shows a lot of deviations from the exact results expected. And the off-diagonal expectation values are something that aren't easily obtained directly from the data. So this gives you an idea of how we use generative models, to enhance experimental abilities or to probe and to characterize the experiment. Because really, the blue points are kind of the off-diagonal expectation values coming from the experiment, which are processed through this model, and the red are our expectations for the device. So I like to show this plot. It never made it into the publication because when I showed the group, they fixed whatever was going on with these deviations here. But it's just an example of, I think, how this can be used. Couple questions. Andre?
Would you expect that if you increase number of atoms, your RBM predictions become more accurate or not with the size?
Well, the problem is if you increase the number of atoms, the number of shots is hard to increase proportionally. So you have to increase the number of shots in order to be informationally complete. So 3,000 shots is good for 8 atoms, but it's not good for like 250 atoms is the problem. So then the reconstruction actually gets worse because you don't have informational completeness. So the RBM works, I think, fine in these types of cases, but there are some limitations, I think, as you scale bigger and bigger, both with data and with the architecture. So we have scaled this up to 256 atoms, but we've actually switched from using RBMs to language models because they scale better. So this is just the first example.
Yeah.
Dennis?
Quick question about the stochastic Hamiltonian. I didn't understand where this assumption is coming from, or why is it physical to use it?
Okay, so I wasn't gonna say too much about the Hamiltonian, but if the off-diagonal matrix elements of a Hamiltonian are non-positive, and I have the wrong sign here, but I can do a simple unitary to change the sign. So if I have a matrix and the off-diagonal matrix elements are negative or 0, then by the Perrin-Frobenius theorem, the extremal eigenvalues are always real and positive. So that means the ground state is real and positive. So it means it has no phase. So that's what we call stochastic. Oops. I clicked on stochastic. So there's a Q there. Isn't that dumb? Somebody made up this word. It means like quantum stochastic.
Okay. So this is just this property of this particular. Okay, I see.
Yeah.
Okay, thanks.
It's only a property of the Rydberg atoms, which is why I didn't want to dwell on it. But honestly, it's another reason I love the Rydberg atom Hamiltonian. It's because it guarantees that I have a real positive wave function. Yeah.
In the ground state, right? In the ground
just
state.
For the ground state.
Yeah.
So yeah, for the physics audience, I should have been more clear. If you have an ion trap or if you have a superconducting qubit, this is violated. And then you need data in multiple bases. But it just so happens that in the Rydberg atom experiments, the basis of the occupation number is informationally complete in the sense that in that basis, my Hamiltonian is stochastic. So this is basically my last slide here. Tying this all in, we had between 2019 and 2024, I don't know, we have a dozen papers on developing language model architecture. So we went from the simple restricted Boltzmann machines through a whole bunch of literature, which apologies to my students, I'll just toss aside. And we've actually started using exactly the GPT type transformer model for this. And so now I've actually shown the Hamiltonian, which I should have shown first. So the Rydberg Hamiltonian has this off-diagonal piece, which is so simple. It's like a transverse field that it renders the whole thing what we call stochastic. And then it has diagonal pieces where I showed detuning before, and I have an interaction, which is 1/R6. I haven't even specified it. So n is the occupation number, so I'm diagonal in the occupation basis. And sigma x is just the outer product, GR, RG, so Rydberg ground state Rydberg. So we've started using exactly the transformer architecture, and I'll tell you why, which is really cool. And so we've released this paper called Rydberg GPT. And now everything I've shown you up till now has just been the right-hand side of this architecture, what we call the decoder. Into the decoder goes my shots. Here's my sigma. Sorry, it's my x. And here's my autoregressive sequence. X, 1, 2, 3, 4, 5, 6, all the way up to complete that vector of n qubits. It's of size n. And if I just had a decoder, I would put in that shot and I would output sorry, theta is lambda. I've just cut this from the paper. So theta means all of the parameters in the model. And I have an autoregressive sequence, which is my, in this case, wave function. You know, for the Rydberg case, this is equivalent to the wave function. The left-hand side of this typical architecture is what we call the encoder. The encoder is how you encode a prompt. If I prompt a language model, I put something into the encoder, and then the context is it's encoded and then passed into the decoder. And so then I can prompt the thing to output distributions that I haven't trained on. So it's a sequence-to-sequence mapping, which is also very common. In our case, the encoder that we use is the Hamiltonian. So I input all the parameters of the experimental Hamiltonian. So it's the Rabi frequency, the detuning, sort of the deltas are the same here. This is called the blockade radius. A is the distance between the optical tweezers, my interaction matrix, and I even use a fictitious like temperature scale here. I input those parameters. They are input and pushed through a graph neural network. They're compressed into a multi-headed attention, passed through a feed-forward neural network. That context vector is then passed into the decoder. Rydberg GPT, baby. Check it out. This is a small language model, I would call it. I show parts of the paper. There's only 66,000 parameters in this thing. And we trained it on a batch size. We have Rydberg atom data. I can't remember how much. We trained it on batch sizes of about 1,000 using an atom optimizer. And I've actually made both the architecture. This is no longer private. You can just Google it. And we've made the data sets available through PennyLane, through Xanadu. So this just came out basically last week. So we've now adopted the idea of let's build an open source language model based on quantum computing data. So why is this powerful? So just like I showed you in the previous slide, what I can do is I can take the input-output pairs, so the Hamiltonian and the ground state shots. So think of it like that. I'm solving the Hamiltonian ground state problem. Here's my Hamiltonian. You know, here is a sample of the projective measurements, and I'm feeding those into the encoder-decoder architecture. And those are my red X's here. So the training points on these plots, and this is a plot of the energy, the expectation value of, the off-diagonal, whatever, sigma X, if I want to call it. Here's a staggered magnetization, spin up, spin down, spin up, spin down. And I've trained the thing on X. Oh, I have a question from Alexander. I'll take that right now.
I have a question. Here on the right, you show very nice fitting between training and inference data. So there is absolutely no overfitting, yes?
Absolutely no overfitting. Okay, yeah, so I'm going to say yes, and I'm going to tell you why I think that's true. So I have training and inference, okay? So this is a sequence-to-sequence mapper here. So the Hamiltonian parameter that I'm varying in these plots is the detuning delta. So I mix large and small delta. So let me go back here. So what I'm really doing is tuning across this phase transition from disordered, where everything is in the ground state, to one of the staggered magnetization states. It's actually a two-dimensional version, but it doesn't matter. I've only trained this thing on the red points, okay? So the red point means that I might take a delta of, I don't know, 1. So, and I input it into the encoder. And then I input a whole bunch of, let's call it experimental data, but I trained from synthetic data in this case, into the decoder. So I do that in all of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 red points. I train a model. I call it M1. That model took, I think, 85 hours on an NVIDIA A100. That's it. We only train for a fixed amount of time. And I can produce many different models with different training sets. But, just as an example, those red points are the training points. After the thing is trained, so after I've stabilized, I've done the training, I can then input different Hamiltonian parameters into the encoder. and I can output the decoder, the probability distribution, and calculate these estimators, and that's the blue points. So to answer your question, no, I don't believe I'm overfitting because the blue points have not been seen in training. The blue points are new parameters that the model has never seen before. And as you can see from the energy, from the off-diagonal magnetization, it's not perfect, and the diagonal stagger magnetization, these points that are out of distribution fit very well to the exact value, which I calculate with quantum Monte Carlo. So I know in this case the exact value. Does that answer your question?
That's very nice. Thank you.
I'm glad you think so. No, thanks very much. Yeah, so I think this is really cool. I think this is what I'm showing you essentially is that, and this is a very simple example. It's a small language model. Again, 66,000 parameters in the model. Trained on a subset of the data, which I've made available. Anyone, if you have a bunch of A100s, you can produce your own model. I've trained it on one NVIDIA A100 for 85 hours to produce model M1, and we have some other models in the paper. And this is how well it generalizes to Hamiltonians that have not been seen before by training. So if you think about the implications of this, the beauty is that I can go to Misha Lukin and I can say, here's model M. Is it M1? Is that what I'm covering it up? Here's model M1. I've trained a transformer on a whole bunch of, cold, whatever, neutral atom data at these points. Now, you can take that model and you can adjust your experimental knobs, whether they're detuning, whether they're Rabi frequency, and you can ask the model to output the expectation value of any physical observable at a different point in phase space. And it might not always be perfect. Like in the off-diagonal case, you see that it's not perfect down here. It underestimates a little bit. But I also believe that this is systematically improvable. So as I train, more and more data, as I get more and more A100s and I push more and more data through this model, I believe that the performance is good enough that I can expect this thing to just get better and better as I scale it upwards. And so that's my final message of my talk, essentially, is that this allows us to, kickstart this virtuous circle, right? Where I have a quantum computer, and the quantum computer produces data, and it produces some limited amount of data, I don't know. And I take that data and I train a language model with it. So what I showed you is two different things. With the restricted Boltzmann machine, really what I'm doing is I'm kind of interpolating, distributions, measurement distributions that I've already seen in order to enhance them, in order to characterize the machine, and also to do some things like certainly control and so on. But what I showed you with the GPT architecture, the sequence-to-sequence mapping, is I can also use language models to do extrapolations to other parameters that the quantum computer hasn't seen before. Okay. And so what that allows me to do is to explore other quantum computing designs. So I can explore different regions of the phase diagram in this case. And that allows me to do different things. It allows me to maybe understand some of my errors. But it very much allows me to iterate design. And so I can iterate the design. And what I didn't show you is I can also predict the behavior of larger qubit systems based on smaller ones if I train enough. And so then I can iterate design, produce a new quantum device that produces data, feed a new language model, interpolate, extrapolate, characterization, control, and design. So this is my message. I think that we're in an age of quantum computers where we can basically start scaling language models. And the Rydberg atoms have been a very good test bed. Again, they are stochastic, and so they're very simple. They're informationally complete. But I'm also very excited about these other architectures that I showed up here, in particular the ion traps. And so the ion traps produce Hamiltonians that are not stochastic. And so in order to be informationally complete, you need measurements in multiple bases. And so what open quantum design is a effort at the University of Waterloo to build an open source quantum computer based on ion traps. It's as simple as that. And so what I hope to do in the future is to take this philosophy of building language models from quantum computing data and build the hardware that'll go on the left-hand side here. So we're going to have open source trapped ion quantum computing hardware producing data that can be used to train open source language models. And through that, I hope this vision of kickstarting a virtual cycle of quantum computer development, together with language models, can happen in earnest. I think I'll leave it there. Happy to take questions or to have some discussion. But I think this is basically my main point, is that I think we're at a very interesting age of scaling language models for quantum computing. So thank you very much.
Thank you, Roger, for very inspiring conclusion. So we are open for questions.
I have a question. Can we go back to the previous slide? So if say I remove the training points that are towards the end, the red dots, if I remove the red dots towards the end and keep the training points, all the red dots till the middle, is the model going to extrapolate? Because as far as I understand, extrapolation is something that neural networks and all these things, I think they cannot do, and removing these training points might hamper the whole model, and it will kind of work well from the range till the training point, but not beyond that. Any comments on that?
I understand what you're asking. The short answer is you can train this model yourself in 85 hours on an A100 and explore that. So we haven't tried that. We concentrated points here because that's the phase transition, and I thought that's going to be the hardest place to learn. And so these are deep into the ordered phase. These points here and these points on the right, they're deep in the ordered phase. And so they're, we believe, easier to learn the distributions. But also be careful what you mean by extrapolation and interpolation. On this plot, it's very clear that I'm interpolating here and I would be extrapolating here. But both of those distributions that haven't been used in the training set are out of distribution for the model. So both of those are actually extrapolation. What we have here is a very high dimensional space. I'm only showing you the delta axis, but I have omega, delta, tweezer, distance, A. I have all the interactions which depend on the geometry of the lattice. I even have temperature. That's a higher dimensional phase space. And the concept of in extrapolation or interpolation, I think you have to be a little bit careful about in these higher dimensional spaces. So I would argue that all of these are out of distribution. Maybe that's the more precise way of saying extrapolation there. So we have no idea how these models behave. That's up for the community to discover.
So one more question, like large language model, they have issues with some call it like AI hallucinations or something like that when you use a lot of data. So I think this kind of hallucinating things might creep into these models also, if we use the traditional transformer and based models with self-attention. What's your comment on that?
Yeah, I guess you could argue here that we're hallucinating down in the regime of sigma x expectation value that doesn't work very well. I think, again, that's, I don't know. I think we have an opportunity to make those concepts precise. I would say hallucination, I get what it means in conventional industry applications. But here, when we're comparing energies, we're comparing correlation functions. These are kind of the base ground truths of the things that we're interested in when we're talking about quantum systems. I think what will come out of this is precise notions of where models fail and what hallucination means here. So yes, I don't disagree. I think there will be hallucinations, but I think we'll be able to define what they are, hopefully.
Thank you. Thanks a lot.
Thanks for your question.
May I ask a question regarding these figures? So
absolutely.
Yeah, you show the expectation values, but from condensed matter physicist perspective, you would be interested also in correlation length analysis, especially you trained in the region of phase transition. Have you tried to look at this?
We haven't with this yet, because I think what we need to do to get a reliable correlation length is a fairly consistent finite size scaling. So in the data set, I do have different sizes. Oh, I don't have the plot. I should have put a plot up. But so the system size is encoded in the VIJ matrix. So it's all-to-all interacting. And I think we trained on system sizes from 5 by 5, so 25 sites up to, I'm going to guess, about 256. So we have a variety of system sizes in the data set. And so, yeah, you could take all those different sizes, put them in the model, and then ask the model to infer. Yeah, so the beauty, and I should have brought the plot, but if you read the paper, you'll see that we can extrapolate in system size. I don't know if it's very accurate. It depends, again, on how much training you want to put through this thing, how many A100s you have. But that would allow you to do very consistent finite size scaling, and then to get the critical correlation length and to get the critical exponents. So that certainly would be super interesting. This is the 2 + 1 dimensional Wilson-Fisher fixed point for the condensed matter people. So it's interesting because it's the first time a 2 + 1D quantum critical point's been seen in an experiment, according to the Harvard folks. So it's very interesting to think about extracting the critical exponents from experimental data.
Yeah, exactly. Denise, please.
So I wanted to ask about the computational cost of running, fitting this model. Like if you, for example, do the same calculation using Monte Carlo, does it give us any computational advantage, like just pure running time? Does it make sense to fit this model first and then extract all these quantities, or rather than just directly calculating lots of them?
Got it. Yeah, good question. That's a great question. So you can ask that question on both the left-hand side here. So on the left-hand side, we took data, we did data-driven, machine learning, and then we inferred, a whole bunch of, we generated data from the restricted Boltzmann machine and calculated the estimator. And then you can also imagine the exact as being coming from quantum Monte Carlo. In the case where I have a stochastic Hamiltonian, I have quantum Monte Carlo. I'd say generally it's all, and I love quantum Monte Carlo. I did my PhD on it. So I generally believe if you can do quantum Monte Carlo, you should do quantum Monte Carlo. I think it's the best tool we have. There are cases, and actually the Rydberg atoms are interesting, where you have frustration and so on, where the Monte Carlo may not work all that well. And then there may be an advantage to the autoregressive models because you're not sampling the Markov chain. You have no autocorrelation time. But R and N's have an inference time of n, where if you have n qubits, transformers is n squared. So the n squared inference of a transformer could actually inhibit sampling. So people are studying other models that have faster inference. But I think the point is we're mostly interested in the cases where we can't do Monte Carlo. So yes, I can do it for Rydberg atoms, but if I get to, trapped ion quantum computers, or if I get to superconducting circuits, if I have a phase in the wave function, I can't do quantum Monte Carlo. So my scalable method is gone now. All I have is DMRG, things like that. So what I really hope to do is, again, get data from quantum computers that can't be simulated exactly. And so the black box, the quantum computer itself, becomes very valuable in terms of producing this data. And so it becomes integrated into the simulator. And so in that case, then I think the inference that you get from the model will be unique. It's something that you can never get from something like quantum Monte Carlo or DMRG. So I think that's kind of the aspiration here. I hope that answered the question. I don't know. Maybe
No,
I missed.
it did. And follow up immediately. What about like, fermion sign problem and all these things, orthogonality catastrophe? If we ever get to that, like, will it have some kind of ramifications for that architecture, in your opinion?
100%. I mean, again, my PhD advisor was Doug Scalapino at UC Santa Barbara, who exclusively almost worked on the Hubbard model. And when I was a PhD student, we talked about the sign problem, the fermionic sign problem. And he told me, Roger, don't waste your time working on the sign problem. It's impossible to solve. But I think one of the aspirations, and just let me go flip around a bit. I think one of the aspirations of quantum computers here are to, simulate the Hubbard model, say, in a quantum device where it's natural, where you don't have to do, classical sampling, that explodes exponentially or something like that. And so again, my hope is that, say, in Marcus Greiner's lab at Harvard or some other cold atom lab, where someone has built a quantum computer capable of simulating or emulating the Hubbard model, my hope is that that can be plugged into this part of the virtuous circle, so that the data coming out of that thing, will be unique and valuable. And so as long as I can learn the amplitude and the phase, like I do in maybe some of these architectures here, so as long as I can learn the full state, or maybe the density matrix that we have other architectures for, from that data, apologies to my advisor, but I think this is the way that we solve the sign problem, is we incorporate the quantum computer into the simulation directly. And so, yes, I do hope someday we can solve all of these hard problems with this type of hybrid architecture.
Thank you very much. Wonderful talk.
Thanks for your questions.
So please, are there any other questions from audience?
And let me give a final plug if you're interested in what we're doing. I gave you some open source links, but also keep an eye on what we're calling Open Quantum Design, which is the hardware effort behind all of this. So we hope to combine hardware and software into a whole open source ecosystem. And we do hope to invite people from all over the world to contribute to this effort to build open source quantum computers and to scale them. And I genuinely hope that Ukraine and Ukrainian scientists can be part of this going forward. So if you're interested in, please reach out on Open Quantum Design.
Great, thank you very much.
Thank you very much.
Let us thank the speaker again for wonderful talk and patient answer session. So
thank you.
Yeah, thank you very much. From now on, we can